So finally, we're ready to start testing our research questions statistically. While it took us a while to get here, our earlier steps should never be avoided. That is, no matter how sophisticated you may become as a quantitative researcher, you'll always need to examine your codebook, manage your data, and examine descriptive statistics for the variables of interest.
In the description of hypothesis testing, when we looked at the association between depression and smoking, we were working with a categorical explanatory variable, the presence or absence of depression, and a quantitative response variable, the number of cigarettes smoked per month. When you're testing hypotheses with a categorical explanatory variable and a quantitative response variable, the tool that you should use is analysis of variance, also called Anova.
Now that you understand in what situations you would use Anova, we're ready to learn how it works, or more specifically, what the idea is behind comparing means. The test that you'll be using is called Anova F-test. So let's use another categorical to quantitative research question.
Is academic frustration related to major? In this example, a college dean believes that students with different majors may experience different levels of academic frustration. Random samples of 35 individuals, each of business, English, mathematics, and psychology majors, were asked to rate their level of academic frustration on a scale of 1, the lowest, to 20, the highest.
This figure highlights that we'll be examining the relationship between major, our explanatory or X variable, and frustration level, our response or Y variable, to compare the different means of frustration levels among the 4 majors defined by X. The null hypothesis claims that there's no relationship between the explanatory and response variables X and Y. Since the relationship is examined by comparing the means of Y in the populations defined by the values of X, no relationship would signify that all the means are equal. Therefore, the null hypothesis of the F-test is population mean 1 equals population mean 2 equals population mean 3 equals population mean 4. Here, we have just one alternative hypothesis, which claims that there is a relationship between X and Y, the explanatory and response variable. In terms of the means, it simply says the opposite, that not all of the means are equal, and we simply write H subscript A, not all the population means are equal. There are many ways for the population means not to be equal. We'll talk about that later. For now, let's think about how we would go about testing whether the population means are equal. We could calculate the mean frustration level for each major and see how far apart those sample means are, or, in other words, measure the variation between the sample means. If we find that the 4 sample means are not all close together, we'll say that we have evidence against the null hypothesis. And otherwise, if they are close together, we'll say that we do not have evidence against the null hypothesis. This seems quite simple, but is this enough? Let's see. It turns out that the sample mean frustration score of the 35 business majors is 7.3. The sample mean frustration score for the 35 English majors is 11.8. The sample mean frustration score for the 35 math majors is 13.2, and the sample mean frustration score for the 35 psychology majors is 14.0. Here's a graphical representation of 2 hypothetical data sets taken from 2 different populations. For instance, students in country 1 and students in country 2. In our hypothetical samples, the means are the same, but they appear in this box plot very differently. A box plot is a convenient way of graphically depicting groups of numerical data, including such descriptive information as the smallest observation of the group, the mean and median, the largest observation, and the spread or variability of the values. The top of the line that sticks out of the top of the box plot and the bottom of the line that sticks out at the bottom of the box plot are the highest and lowest values. The red dot is the mean. The middle horizontal line is the median. You can see that each data set has the same set of means, and thus the same differences among them. That is, students in Country 1 and students in Country 2 both show data for 4 groups with the sample means of 7.3, 11.8, 13.2, and 14.0, indicated with red marks. The important difference between the two data sets is that the first represents data with a large amount of variation within each of the 4 groups. The second represents data with a small amount of variation within each of the 4 groups. Box plots for Country 1 show plenty of overlap among the 4 groups because of the large amount of variation in frustration scores within the groups. One could imagine the data arising from 4 random samples taken from 4 populations, all having the same mean of about 11 or 12. The first group of values may have been a bit on the low side, and the other 3 a bit on the high side, but such differences could conceivably have come about by chance. This would be the case if the null hypothesis claiming equal population means were true. Box plots for Country 2 show very little overlap because of the small amount of variation in frustration scores within the groups. It would be very hard to believe that we're sampling from 4 groups that have equal population means. This case is an example of when the null hypothesis claiming equal population means would be false. The question we need to answer with the Anova F test is, are the differences among the sample means due to true differences among the population means, or merely due to sampling variability? In order to answer this question using our data, we obviously need to look at the variation among the sample means, but that's not enough. We also need to look at the variation among the sample means relative to the variation within the groups. So F is the variation among sample means divided by the variation within groups. In other words, we need to look at the quantity, variation among sample means, divided by variation within groups, which measures to what extent the difference among the sampled groups means dominates over the usual variation within sampled groups, which reflects differences in individuals that are typical in random samples. When the variation within groups is large, like in Country 1, the differences or variation among the sample means could become negligible, and the data would provide very little evidence against the null hypothesis. When the variation within groups is small, like in Country 2, the variation among the sample means dominates, and the data have stronger evidence against the null hypothesis.
Looking at the ratio of variations is the idea behind comparisons of means, thus the name analysis of variance.
Here are the results of the analysis of variance for Country 2, testing the relationship between major and frustration score. The F statistic, circled in red, is 46.6. Since we know this is the variability among sample means divided by the variability within groups, this large number suggests that the variability among sample means is much greater than that within sample groups. The p-value of the Anova F test is the probability of getting an F statistic as large as we got, or even larger, had the null hypothesis been true. That is, had the population means been equal. In other words, it tells us how surprising it is to find data like those observed, assuming that there is no difference among the population means. This p-value is practically 0, telling us that it would be next to impossible to get data like those observed had the mean frustration level of the 4 majors been the same as the null hypothesis claims. The p-value of 0.0001 suggests that we will incorrectly reject the null hypothesis 1 in 10,000 times, and we will be correct in accepting the alternate hypothesis 9,999 times out of 10,000 times. So we can confidently conclude that the frustration level means of the 4 majors are not all the same, or in other words, there's a significant association between frustration level and major. So we accept the alternate hypothesis and reject the null hypothesis.
The F-test and the p-value do not provide insight into why the null hypothesis can be rejected because there are multiple levels to my categorical explanatory variable. They do not tell us in what way the population means are not statistically equal.
Note that there are many ways for population means not to be all equal. Having each of them not equal to the other is just one of them. Another way could be that only two of the populations are not equal to one another. In the case where the explanatory variable represents more than two groups, a significant Anova does not tell us which groups are different from the others. To determine which groups are different from the others, we would need to perform a post hoc test. A post hoc test conducts post hoc paired comparisons. Post hoc means after the fact, and these post hoc paired comparisons must be conducted in a particular way in order to prevent excessive type 1 error. Type 1 error, as you'll recall, occurs when you make an incorrect decision about the null hypothesis. That is, you reject the null hypothesis when the null hypothesis is true. Why can't we just perform multiple ANOVAs? That is, why can't we just subset our observations and take two at a time? That is, compare white versus black, white versus American Indian, Alaskan Native, etc., until all the paired comparisons have been made. As you know, we accept significance and reject the null hypothesis at p less than or equal to 0.05, a 5% chance that we're wrong and have committed a type 1 error. There's actually a 5% chance of making a type 1 error for each analysis of variance that we conduct on this question. Therefore, performing multiple tests means that our overall chance of committing type 1 error could be far greater than 5%. Here's how it works out. Using the formula displayed under this table, you can see that while one test has a type 1 error rate of 0.05, by the time we've conducted 10 tests on this question, our chance of rejecting the null hypothesis when the null hypothesis is true is up to 40%. This increase in the type 1 error rate is called the family-wise error rate and is the error rate for the group of pair comparison.
Post hoc tests are designed to evaluate the difference between pairs of means while protecting against inflation of type 1 errors, and there are a lot of post hoc tests to choose from when it comes to analysis of variance. There's the SIDAC and the Holm t-test and Fisher's least significant difference test, Tukey's honestly significant difference test, the Sheffey test, the Newman-Cools test, Dunnett's multiple comparison test, the Duncan multiple range test, and the Bonferroni procedure. It's enough to make your head swim.
While there are certainly differences in how conservative each test is in terms of protecting against type 1 error, in many cases, it's far less important which post hoc test you conduct, and far more important that you do conduct one. We've covered a lot of information, so here's a quick summary of analysis of variance. First, an analysis of variance is used when we have a categorical explanatory variable and a quantitative response variable, and we want to examine differences in the mean response variable for each category of our explanatory variable. The null hypothesis is that there's no relationship between the explanatory and response variable. In other words, that all means are equal. The alternate hypothesis is that not all means are equal. The F statistic is calculated by comparing the variation among sample means to the variation within groups. If the variation among sample means wins out, the p-value will be less than or equal to 0.05, and we have a significant finding. This would allow us to reject the null hypothesis and say that the explanatory and response variables are associated. Now you're ready to test a categorical to quantitative relationship. If your own research question does not include these types of variables, you might want to test the procedure with variables from your data set that do require an Anova. For example, you could look at mean age differences according to any categorical variable in the NESARC, or treating the grade level variable and add health as quantitative, you could look at mean differences in grade level, again, by any categorical variable that you choose. For both Gapminder and the Mars crater data, there are many quantitative variables, so you might choose to categorize one of them for inclusion in an Anova. whatever types of variables you have, you'll be able to test the association with the right tool.